The idea was to look at large language models, but those that are not too large, because extremely large language models are notoriously hard to operate. They typically have hundreds of billions of parameters. So, for example, ChatGPT version 3.5 was derived from GPT-3 and therefore had 170 billion parameters. And if you want to operate such a large language model, if it would be available, then it would require multiple costly GPUs. So several A100s or H100s. And that would not only mean large costs, but also slow inferencing, despite the large number of GPUs. And therefore, smaller models are desirable that can also be run by smaller companies, which are the smaller budget. And looking at the literature showed that there are some promising results of scaling down language models by retaining the good results. For example, Chinchilla from DeepMind was one initiator of that research in that direction. So initially, language models grew larger and larger because better results were obtained with more parameters. But then some upper bound was reached, and now there is more research in the direction of having smaller models with equally good results. So therefore, we defined the term medium-sized language model. In the papers, the term large is not really well defined. And therefore, for our paper, we defined medium-sized language models as those that had at least 6 billion parameters, but less than 100 billion parameters. And looking into publicly available language models that fall into that range, we found 4 different classes. So 7 billion parameters is a very well-researched area. Then some models in the area from 10 to 13 billion parameters, around 30 billion parameters as the third class, and 60 to 70 billion was the last class that we found. The evaluation of these kinds of models is also well studied. So there is a large number of standard benchmarks that are typically applied. But the benchmarks are designed in a way so that they are automatically evaluated, which means that they typically ask multiple choice questions or yes/no questions. And we found that this is not a good way of evaluating these models, because they are also designed for open-ended generation of text. And there is no good benchmark available for open-ended questions. So we constructed our own data set with 110 questions in different categories. And I've listed the categories here together with one example. So we also tried to think of own questions that are not already represented in the internet, and therefore potentially the training data of that models, although it cannot be excluded that still the training data of some of the models that we tested contains similar or equal questions, especially in the trick questions category. So we included some trick questions that are meant to fool humans. And the hypothesis was that large language models can be fooled in a similar way, or medium-sized language models that we evaluated. And other categories that we included are math word puzzles, but with a emphasis on understanding the words and not so much with an emphasis on calculation, because it's already known that large language models struggle with mathematical calculations, and therefore we didn't want to stress that factor in the evaluation of medium-sized language models. So some of the math word puzzle questions that we included can be answered without any calculation. You see it in this example here. It's just relational reasoning and no math included. Yeah, and then we also included questions that require different forms of reasoning, hypothetical questions, and also questions that involve symbolic reasoning, where we use a variable to indicate something. And yeah, that concluded the dataset that we constructed. As I said, the idea was to perform human-based evaluation, because open-ended questions are hard to evaluate automatically. Typically, for other tasks that are evaluated, like summarization, you have metrics like bleu score or rogue score that are used, but they do not capture the semantic meaning of the results that are generated, but only concentrate on overlap regarding the wording. And since this is can be varying for open-ended questions, these scores do not really capture the good or bad results, and especially not exact match. These measures cannot be applied to open-ended questions. Also, the length of the answer needs to be taken into account. Sometimes the models, for example, output the question before answering the question as part of the answer. And that also makes it harder to evaluate the results. So we choose human-based evaluation, and the choice of models. So the was done based on these criteria here. So Hugging Face was the main source of getting the models. And the evaluation period initially was from December 2022 until June 2023. We only evaluated publicly available models, which excluded, for example, Peinl and Anthropic. We concentrated on English language models, either those that are only trained in English or those that are trained with English and other languages. Of course, we only analyzed those models that fall in the parameter boundaries that we've defined. And as a reference for the performance of the medium-sized language models, we also included two large language models, ChatGPT 3.5 Turbo, which was the reference in January 2023 when we evaluated that, and GLM, which is a Chinese and English model, because it was explicitly tailored to be runnable on a single A100 card, and therefore we also included that in the evaluation. All evaluations were done on an 80 gigabyte A100 card, and ChatGPT was evaluated through the web interface. We also collected a human baseline, because typically, if you don't have that, the expectation is that humans can answer 100% of the questions, because human thought of the questions, though they are also able to answer them. of course. But if you take individual humans, then this expectation is certainly wrong, and we rather expected something of like 90% as the answer rate of humans. So our sample was from students and university staff members, so people with a higher education and either pursuing their bachelor's or master's or already having graduated from a bachelor or master study program. We collected them with different backgrounds like computer science, business administration, engineering, and some other backgrounds. Altogether, we had 87 participants with 41% female and 54% male. The rest had no answer to the question. And overall, we had a dropout rate of 8.4%. So people that started the questionnaire but did not finish it. And most participants were students, which results in a low medium age of 23 years as a median and 25.8 years as an average, which shows that there are some older participants that increase the average. Astonishingly, the average human score was only 70%, so much lower than our expectation, which shows that the dataset is really challenging, not only for the AI, but also for humans. The overall result is compiled in this diagram here. I colored the model classes with different colors as shown in the legend here. There are some bars that are not with solid color but dotted. These represent models that were not instruction tuned but are just basically pre-trained models without any fine-tuning on either question answering or instruction datasets at all. And you see that some of them still perform quite well. So the initial hypothesis was that pre-trained models without any fine-tuning will not perform well. And, that can be seen, for example, with some of the opt models that reached less than 20% accuracy. But as I said, some of the models still showed better results, like GLM 10 billion parameters or Llama 13 billion parameters that nearly reached 40% without special fine-tuning. The best performing models of each size category are shown with the exact percentage of correct answers. So answers were rated either correct or incorrect. There was no in between. And you see that larger number of parameters usually also means better performance, but with a few notable exceptions. For example, the best performing model overall was a model with 33 billion parameters. And this model even outperformed the human baseline for a small margin. And it also outperformed its larger counterpart. So Ouroboros is the model name, which also stands for the data set that it was fine-tuned. So most of the models that you see are based on the Llama base model, foundation model. Few of them are based on other architectures like T5 or MPT. But most, as I said, are based on Llama, and only the instruction dataset differs. Astonishingly, the 33 billion parameter model outperformed the 65 billion parameter model, although both were fine-tuned with the same data set and are also based on the same pre-training data. All these models, or both these models, outperformed also ChatGPT, which served as a reference, which scored impressive 60.9%. But was still below the human baseline of 70%. Let's go into some more detailed evaluations for the different classes. In the 7 billion parameter class, Alpaca was the initial driver for this kind of instruction tuning, based on input from data that was generated with GPT. So not human generated, but LLM generated. And the researchers from Stanford that proposed this Alpaca approach did not open source the model, but only open source the data set and the approach. And therefore, soon several open source models were created that tried to mimic that approach. And you see that not all of them are able to reach the good results of the original Stanford model that was reported in the paper. But there are some that are similar. And we included two here, one that only had a medium performance, not much better than the Llama pre-trained model itself, and one that really was on the top of the 7 billion parameters list and only outperformed by the Wizard LM language model from Microsoft, which was the best performing 7 billion parameter model until June 2023. In the 10 to 13 billion parameter size, the T5 models that were fine-tuned either on instruction data like FLAN T5 or on closed book question answering like the ones shown on the right below, the SSM TQAO and the TQAO itself. So they are also not fine-tuned on instruction data, but fine-tuned on closed book question answering. And you see that they also perform relatively well, although they are outperformed by Llama-based 7 billion parameter models with good instruction tuning. So the best performing models in the this category here also are Llama-based. One from a French research group with a data set called Johannes, and the other one from is called Minotaur. And both reached impressive 56%, which is nearly 10% better than, or 9% better than the best 7 parameter billion parameter models. Since there were not too many, we summarized both 30 billion and 60 billion models in one category here, in one table. Since also the performance was similar, as I already said. And you see that the best performing models in the 30 billion category were also outperforming ChatGPT, not only Ouroboros, but also Lazarus, which indicates that it was not a single mistake, but it's the potential is there to outperform ChatGPT with 170 billion parameters with as few as 30 billion parameters. Overall, the performance of the really big models was less than expected. Dromedary from IBM with 65 billion parameters is one exception that performed relatively well. But if you look, for example, at Opt, 66 billion, and also the Luminous models from the German company Aleph Alpha, which are reported to have 70 billion parameters. Their results are not as good as we had expected before. Since the review in other journals took some time, we did an update in December to reflect the latest developments in this space here, with an emphasis on new 7 billion parameter models, but also including some new model architectures like Yi and Mixtral. We also included for reference one smaller model that does not fall in the medium-sized category, which is Phi-2, which is reported to be able to compete with 7 billion parameter models, although having only 2.7 billion parameters on its own. Therefore, we included this as well. And most of the new 7 billion parameter models are based on Mistral, pre-trained model from a French company. And you see that also newer fine-tuning approaches are included, like DPO, direct preference optimization, and one model that was created by merging other fine-tuned models called Neural Chat, and also other new fine-tuning approaches like Orca2 from Microsoft. And as you see, the results in the 7 billion parameter category are much better than they were in the period until June 2023. So there was a huge leap from 47% accuracy to 58% or 59% that you see here for Mistral, 7 billion DPO, and also for Neural Chat. So these outperform the best 13 billion parameter models from June. And also the Dolphin dataset that was trained together with the Yi model architecture did a very good job with 62% accuracy, so better than ChatGPT from January 2023. And the best overall model, as expected and also reflected on other public leaderboards, came from Mixtral, which is a mixture of expert-based model that is constructed from 8 so-called experts, so model parts that act independently. It's a sparse model architecture that only activates parts of the overall parameters. So it needs a large GPU RAM to hold all the parameters, but the inferencing is much faster than similar sized models with dense parameters, because only parts of the parameters are really active, which speeds up inferencing time. So in this update, we also included the inferencing time. Most of the models were evaluated in 4-bit accuracy, with the GPTQ quantization mechanism, as you see in the model name. Some were evaluated in FP16, like Phi2. One model was evaluated with FP32. And you see that this has a dramatic result on the inferencing time, which is overall very good. So either 3 or 6 minutes to answer the 110 questions, with the exception of mixed RAL, which results in a much larger inferencing time, but also with better accuracy. Nevertheless, I would have expected even better accuracy than 63%, although it's still the best performing models, excluding Ouroboros 32 billion. I would have expected an even better result here. So that brings me to the discussion. So overall, the length of the answers was quite different, and future evaluations should try to include that in the evaluation to have a penalty for unnecessary long answers. Also, repeating the question of as part of the answer is an undesirable behavior that should not be included in future models. So that's of course part of the training data as the instruction tuning takes place. Some models also showed the behavior of asking own questions, either after answering the original question or sometimes also instead of answering the original question. That seemed to be kind of the LLM way of saying, I don't know. So that's the last point here, confessing that the model is not able to answer the question is one of the weak points. We only had one model in the evaluation that was doing that. All the other models rather hallucinated and answered something wrong. And some of the less good fine-tuned models also generated answer candidates before really giving an answer. And sometimes that also led to the fact that the answer was not included in the, so that the character of the answer that should be given at the end was not included in the answer anymore because previously the model ran out of tokens and hit the max new token limit that we gave. Some limitations. So the evaluation was only done by the two authors of the paper. There was no cross-check with others, and there was also no cross-check with LLM as a judge. That's the typical way of evaluating open-ended questions today, which has its own limitations, but still is the best automated way of doing an evaluation currently. We also did not test different prompt engineering techniques. So there are a number of well documented techniques that enhance the answer rate and accuracy of large language models, especially chain of thought prompting or self-consistency and approaches like that. We did not do that because we think that the model or a good model also should be able to give good answers without any special wordings of the question. And therefore, we intentionally did not do that. But of course, it would be interesting to check whether that makes a difference in our data set as well. That brings me to the conclusion. So it can be seen that small models get better and better, and the gap to large language models like GPT-4 is getting smaller and smaller. Currently, GPT-4 is still unbeaten by open source language models, but GPT 3.5 is already reached, and especially the breadth of application areas that GPT-4 performs well in is currently one of the advantages of that extremely large model. But the open source community is making tremendous progress. So it's nearly more than 1 year since the release of ChatGPT 3.5. And already now the open source models are outperforming this state of the art from beginning of 2023. And they generate new ideas how to increase the performance further, not only new data sets, but also new training methods. So like reinforcement learning from AI feedback, or direct preference optimization, which is currently the one that seems to generate the best results for open source data sets. And also a new technique called model merging, based on an open source tool called MergeKit, is becoming very popular and gives new room for experimentation and generating even better models with as few as 7 billion parameters. Automated evaluation is still subject to further research because LLM as a judge is the new standard, but still is known to have severe limitations. For example, if you ask the model to compare answers of different other models' output, then it's well known that the first answer is kind of preferred, no matter which answer is the first answer. If there are not huge differences in the answer quality, then the first answer will usually be preferred. And another other problem that is currently visible is that poisoning training data can become a problem. So especially the public leaderboards like Hugging Face and Chat Arena face that problem. They rely on a defined set of evaluation data, and this is maybe included in training data. Thanks for your attention, and I'm looking forward to your questions.